Okay, so hello everyone. Today is the 7th of October 2024, and I'm really happy to present external speaker Anca Nitulescu talking about Flip-and-Prove today. Yeah, without further ado, Anca, the floor is yours.
Yeah, thank you for the invitation and thank you for being here. So today I will talk about recent work, joint work with Nikitas and Carla from Pompeu Fabra University. About Flip-and-Prove R1CS instances. Okay, so just as a first outline of the talk, I will just start with the main idea of our scheme and the motivation to design such a scheme. Then I will show we have two contributions. One is the flip, which is like a folding through inner product arguments scheme. For R1CS, and this is like one part of my talk, and then I will introduce the variation of growth 16 that we need in order to prove these final instances, which are relaxed form of R1CS. So we need to design a new growth 16, which may have independent interest. And I will end up with some conclusion and related works in folding landscape. So first, wanted just to remind people what are zero-knowledge SNARKs, our main topic today. So these are proving systems that are succinct, meaning that the proof size is independent of the NP witness we want to prove. They are non-interactive, so we don't ask any exchange of messages between the prover and the verifier. The proof can be posted independent of any verifier. And there are arguments in the cryptographical soundness sense that they are the soundness holds only against computationally bounded adversaries. And a nice feature that is a stronger notion than just soundness is that we care about the not only the existence of a solution, but about the construction of the knowledge of a solution. So knowledge soundness models the fact that the prover knows the witness of some NP statement, not only that a witness exists. And zero knowledge, it's a property that we can add also, and it usually comes for free by some randomization. And this allows the prover to hide any secret information from the verifier. So the proof should not leak anything more than the correctness of the statement we want to prove. Great. So why we care about zero knowledge and what applications we have? I guess everybody here is convinced that zero knowledge are super useful in the blockchain setting, where we need to allow peers to check validity of some generic statements. So anyone in the network should be able to check the validity of some transaction in a block in order to ensure this soundness of all the blockchain protocol. So I took as an example and motivation the ZK rollups, where blockchain want to scale their bandwidth and the size of the transaction that are posted on the blockchain by using zero knowledge proofs. So executing this transaction outside and not posting them directly on the blockchain, and executing them off-chain, and then just post a proof of the correct execution that allows to update the state of the blockchain. And in this scenario, SNARKs are proving something that a change of state, and this can be translated in a cryptocurrency situation, for example, that some transactions where some state modification is a result of the execution of a batch of transactions that happen off-chain, and execution was done correctly. Okay, so this is what we call layer 2. And what happened in this kind of rollups, what we call ZK rollups, even if not always hiding is the most important property, but scaling, then zero knowledge is not really very important here. So we need to ensure correctness of a lot of transactions. This execution of a transaction is a circuit that looks the same for any transaction. It's only the inputs and outputs that will change. So naively, we can take 100 transactions, let's say, and just generate a proof that all these transactions were correct by writing the whole circuit of all these executions. And this is a long delay. So we probably will need to wait for this prover to compute the final proof in order to allow the next block to be posted, because this takes a long time. And also the verification of such proof may be long, because we need to read all the inputs and to verify the proof. So some other idea is to periodically provide proofs for change of states for a bunch of transactions. We chunk this in multiple transaction bunches, and then we need to post many proofs. But this is faster for the prover, because we prove a transaction as they come, like in less time. So the verifier is slower, because, and also the blockchain will be clogged with all these proofs. Even if they are succinct, having a lot of proofs on the chain is not ideal. We wanted to avoid publishing too much information on the chain. So the open question here in this use case scenario is, how do we prove and scale operation that happened on a side chain, on a layer 2, into the main chain in a very efficient way for the prover, and also saving on the proof size and the verification complexity. And our solution may be one idea of how to solve this. And in brief, what are we doing in Flip? We have multiple instances of the same type that we want to prove. And before I will tell you how we're doing in brief, I will just remind you some already existing solution, and a naive one will be just to prove all of them, as we saw, and have multiple proofs, each proof for one of the instances, and maybe batch verifying them in order to have a faster verification than just checking one by one each proof. So that's one of the easy, naive way to solve. Then what was already proposed in the literature is to first prove them, and because we prove them as they come, so each of the instances, and then because we don't want to post so many proofs, so have a proof size which is sublinear in the number of instances, we will aggregate all these proofs into some final aggregated proof that can be verified in time sublinear of the number of proofs. So that's allowed for faster verification. But a newer strategy was proposed, and this involves recursion. And how recursion will work is we first prove something, and then we allow to prove that we already had this proof and add a new statement. So at each time a new statement comes, instead of re-proving something we prove that this new statement is correct, and that we already had a valid proof for the previous statement. And recursing like that, we can just allow to prove everything sequentially, and not having to read again all the previous statement and proofs. So this is one of the very interesting and kind of orthogonal solution to ours. And then there is folding. So folding came in very many flavors in the latest years. And we have one new flavor of folding. But first, what folding allows to do is to take all these instances, and instead of even proving them at all, just fold them into shorter ones. Like we have two instances, we can fold it into one that has the same size of each of the initial ones. So we fold as we receive instances to be proven. So we fold the instances and the witnesses, and at the very end, the hope is that we will have only one instances and witness to prove and we apply a single SNARK to it and prove once. So that's actually folding. That saves a lot on the prover overhead, because we never prove in this process of holding, we prove only once at the end. Great. So I made a bit of a comparison, but of course there are many schemes with many properties, so I cannot like be very precise, but just as a generic idea, what are the main advantages and disadvantages of these strategies? So in aggregation, actually the proof size is very nice, like it's logarithmic size in the number of proofs to aggregate. Verifier is also logarithmic, of course, but the prover time, unfortunately, is a lot higher than like just doing the proofs themselves, because they have to prove each instance at a time and then do the aggregation, meaning that you add an overhead to this. Okay. Let me know if there are questions. Then in the recursion, we have less ideal proof size sometimes. Sometimes it's logarithmic and some constants, depending on what scheme we use. The verifier time is as well a bit impacted by this size of the proof, and sometimes we don't use trusted setup, so we have linear verifiers in size of some circuit size. And the prover time is better because, as I said, at each time we accumulate somehow the instances to be proven instead of proving them each independently. And folding seems here that looks the best of all because we have very good proof size. The verifier time is very good. Like it's also depends on the scheme we use underneath, but like it's as good as the proof size. And then we have the prover time that where we can gain a lot, because as I said, instead of proving the statements we want, we fold them all along, and we prove them only at the end. So this seems to be the best of the three words. Also some engineering overheads that should be mentioned about these two first approaches is like in aggregation, usually the ones that we know are based on some heavily algebraic schemes like Lot 16. So the prover computes a lot of FFTs for all the separate proofs. So this is a lot of overhead for the prover. And in recursion, there is more of an engineering problem with like these cycles of curves, which are curves that are less efficient than the normal pairing curves that we know. And also they require more engineering involved tools. Okay.
Sorry, can I ask a short question? So I actually must admit, I'm not sure I really understand aggregation, which is the most. My idea from what you're saying is that you're the prover runs the like sub prover, let's say gross 16, like linear number of times, and then you just take a linear combination of the algebraic proofs, and then you like also have a linear algebraic verifier. Is that how it works?
It's a bit more efficient for the verifier. Like verifier is logarithm type, but like your intuition is good. Like as I said, aggregation means that we prove independently each of the statements. So we cut the big computation into identical statements. We prove them independently, and then we aggregate by. And this aggregation is, of course, is linear for the prover in the size of the statement, but has as a result a final proof that is logarithmic in the number of the initial proofs.
Right. Okay. And to verify this aggregated proof, you need to take all these n instances,
yes,
and then also recombine them somehow. So you basically have a recombined aggregated proof, and you have a recombined aggregated witness instance, and then you verify the former with respect to the latter.
That's correct. Like a verifier should read the instances for each of the proof. Like even if the proofs are not sent to the verifier, the instances should be one input of the verifier. Yeah.
But then I would be probably assuming that this is faster than doing recursion because this is still same curve, right? Or why do you say that the proving time here is higher than with the recursion approach?
Because the proving time involves proving each of these independently, and also like it works mostly for growth 16. There is some Plonk also, but Plonk with trusted setup. So yeah, these are a lot of FFTs that we need to prove. Each time we do a growth 16 proof, and then we do some other proof of proofs, which is the aggregation.
Right, I see. Okay.
Yeah,
Okay,
so the overhead is mainly the fact like we start with proving each of the statement rather than accumulating as you do in recursion.
Sounds good. Maybe also a short question: are you comfortable with us interrupting you during the presentation, or
Sure,
would you
sure,
rather have all the questions in the end?
No, I'm happy to be interrupted. Yeah.
Okay, perfect. Thank you.
Yes. So there was another question, or okay, I can continue. So actually, I want to tell you what's the initial motivation we have for this work, which is not really the rollups. I think like that's another interesting use case, but we started it by looking at proof of storage from the Filecoin network. Back then I was at Protocol Labs, which runs this Filecoin network. And here we have storage provider that onboard storage capacity on a blockchain every day in order to earn some block rewards. And all the nodes in the network are supposed to check to ensure that this storage capacity is real and that data is being stored by the storage provider. So the storage provider need to provide some proofs of storage. And proofs of storage is exactly SNARKs. Like we use growth 16, we were using growth 16 SNARKs here. And because it's this storage proof circuit is very complex, computationally heavy, only proving 32 gigabytes on board on the network would require a circuit that could not fit in a single SNARK. So the circuit was cut in 10 individual identical circuits, and each of them was a different instance to be proven. So we need 10 SNARKs for each 32 gigabytes, and of course, prover this puts a storage onboard limit on the storage providers that cannot onboard a lot of storage, because like these blocks will get full of proofs very easily, and then the verification time to check individually each of these proofs will take a lot. So a new block cannot be created too soon. So this will put a big limit on the scaling of such. And the solution that were proposed already were batch verification. So instead of looking at one proof individually, like peers here will nodes in the network will just do batching in order to verify, but still this is overhead in the size of the proofs that we need to post on chain. So another idea was aggregation, and that's SnarkPack, a scheme I co-author that takes different proofs, a lot of proofs, and computes an aggregated proof that is logarithmic size. And as we just confirmed with Misha, that we need to still look at all the inputs of all the instances, but only at the log size n proof as a verifier. So this saves on storage, like on communication size, and also on the verifier side. Okay, so follow-up idea would be to save a bit on the prover's cost, and this was where Flip came in. And Flip has kind of same motivation. So we have these units of storage that we want to store, and each of them is a similar like statement that we need to prove. So we will first just fold them together into a small final statement as we receive them, and then we will have this final proof for a single statement. So the prover only runs one proof, which is the computational heavy part of the heavy cryptographic operation are only in the proof, and then post on the block this final proof. And the verifier who comes will also need to look at all the instances, and they will have only a final proof that guarantees that all these instances were like correctly proven. Okay, so it's the same kind of statement, the setting. And we also think like there may be other applications. I'm happy to brainstorm ideas. Maybe in the ZK rollup setting that I was mentioning before, it makes sense to, instead of proving things, proving transactions, that just hold all the statements we receive, we have on the layer 2, and then just prove a final statement. Okay. So now let's go more into details of what exactly proof systems are used here and what relations we need to fold. So of course, proving we deal with proving NP languages that are efficiently decided with a witness, when we have a witness, and a way to model such a constraint system for such NP languages that capture all the NP. The characterization of the NP that we will use is rank 1 constraint systems, which allows to represent any arithmetic circuit in any arbitrary NP language, because circuit satisfiability is also characterizing all NP. So it's widely used in SNARKs. It's used especially in the state of the art in terms of proof size, the GROT16 proof system. And as I said, it usually comes from arithmetic programs or arithmetic circuits that we want to model. And how it is defined, we have three matrices, A, B, and C, and a vector of Z of instances, X, and W, which are witnesses. So a relation like a Hadamard product between this linear equation, AZ and BZ, which are pairwise product, not a matrix product here, equals CZ. It's like R1CS. And this actually captured all the constraints for all gates, all multiplicative gates here. So any arithmetic circuit can be written like that. And this is what that folding, I will not go into how we write it, but like we write a system of equation, and then we generate these matrices, which are sparse matrices that have rank 1. This is why we call it rank 1 constraint system. So we have this relation at the end that characterizes our circuit that we want to prove. So if we know Z, which is the input and the witness that satisfies such a system, this will convince the verifier that we computed correctly the circuit satisfiability assignment. Okay, so how folding schemes work starting from this? As I said, we never compute proofs, we just fold statements, instances, and witnesses. And at the end, we have one single final folded instance statement that we can prove. And the folding scheme consists in an interaction between a prover and a verifier, where the verifier, of course, only has the inputs, the instances that are to be proven, and the prover has the instance and the witness associated with for some relation. And folding allows the prover and the verifier to compute the folded final instance for the verifier, and the prover will have the folded instance and the folded witness. And the interaction is just by the prover will send some cross term that is needed in order to fold the instances, which the verifier will use. And the verifier needs only to send some random challenge, so the prover cannot cheat in this folding. And we go back to R1CS constraint system, because this is what we will fold later. Okay, I think we need to fold multiple instances. So let's start with two R1CS instances, which are defined by the same. They are for the same constraint system that is defined by A, B, and C as matrices, but we have like these different instances to prove for this relation, Z1 and Z2. So the idea of folding schemes in general is just to take a linear random combination of the two, and this, in the lucky case, this will define a new folded instance. But unfortunately for R1CS, as I defined it before here, this doesn't work. Like, unfortunately, when we sum these two equations together with this random scalar multiplication here, this doesn't lead us to a R1CS. And the reason is written when we develop these two equations here. This is capital Z will be the small z. We wanted it to look like A capital Z, which is a new Z, times B capital Z, equals C capital Z, where Z is ideally should have been Z1 plus R Z2. But unfortunately, when we develop what happens here, this computation here, we will have cross terms. We will have some cross terms that are appearing, and one is times R, the randomness we use, and that's like the cross term, and one is times R squared here. So a nice idea to fix it that was proposed in the NOVA paper is to relax a bit this equation so we can allow for some error from like these cross terms that appear here that annoy us and that don't allow to have what we wanted to. So this is how R1CS looks like. We always start by some 1, and then this is the input, and then this is the witness vector, such that this satisfies the equation between the matrices. And the relaxed R1CS has an instance that starts with some constant u that can be something else than 1, and also has an error, an error vector. And it looks like this Z prime, which is a new vector that starts with a u, a constant u, x as the input, e as an error term, and w as the witness. And it looks like the equation between the matrices for the same matrix A, B, and C looks like this. It has to be equals to some constant times C times Z prime, which is the new vector Z, plus some error vector. Okay. So if you look at it a bit more carefully, we have that if u equals to 1, of course, we get back here. And if the error is also 0, we get back to the R1CS we knew from before. So it's just a generalization of R1CS. And the paper shows that this is also a characterization of MP, and we can use it in order to arithmetize any computation we want, starting with the arithmetic circuit. So now let's convince ourselves that this is the right way to express computation in order to use folding. So if this is the relation we want to prove, now we have one for Z1 and one for Z2 for the same relation defined by A, B, and C, and new errors E1 and E2. And we want to fold it. So when we take Z1 and Z2 like that, from the relaxed R1CS, we have A times Z1 plus RZ2, which is our new Z, Adamo Pro B times the same new Z, equals U prime plus RU2, which is the new U, times C, times the new Z, plus some new error, where we put all the junk terms that we don't like in this when we develop these two here. So yes, when we rewrite it expanded, we will just write everything that we want to get rid of into the error term here. Okay, let me know if you have any questions till now. And because this is still not enough for our purpose, or for our folding, we don't want to have the verifier read any witness, because the witness is the one which is NP, is linear in the size of NP complexity, size. We want to just commit to E and the error term, which is also linearly dependent on the size of the circuit to be proven, and to the witness term. So which we will call committed relaxed R1CS. This is still from Nova. So let's just state what does committed relaxed R1CS looks like. We have an instance which is this constant U, some input X, this is a vector of input, and a commitment to some error under some commitment key. And then we have the vector Z, which is U vector X and two commitments, a commitment to E, a commitment to W. So this is what the verifier will, the prover will have to fold, while the verifier only looks at the witness, at the instance, at the instance. And the relation says that there exists an opening vector E, error vector E for the commitment in red here to E, and an opening W, a vector W, which is an opening to the committed value W in brackets, such that Z vector like that, with these vectors not committed, satisfy the relaxed R1CS equation for A, B, and C. Okay. Yes.
Sorry, Anca, I don't want to be nitpicky, but it's, if I'm not mistaken, in the last equation, the Z should be X, or aren't you need to multiply the matrix with the X, I assume, because the E and U are already kind of inside the Z, or shouldn't be?
You're right, E and W are inside the Z. And this is how R1CS looks like a relaxed R1CS. You have to also write the input inside the
So
vector.
do we put the error inside the column by which we multiply the matrix?
Oh, I see what you mean. Oh, I think this is an error, yes.
Yeah, it seems to be a type, right? It should be A times X times Hadamard product B times X equal to something.
Yeah, the E should not be in Z, right? But let me think. No, I think E is still as X is in Z in the original R1CS, then now E is kind of part of the instance. It is not necessarily something we want to hide from the verifier. It's just for succinctness, we need to commit to it, because if not, then the verifier will have to read something in the size of the. But E is still part of the what we put in Z. Yeah.
Yeah, that makes sense. Thank you.
Yeah. Yeah, remark that here E is of a different, it's a vector of a different size than W, for example, because it's like these matrices are not squared matrices. Okay, so this is how the NOVA protocol looks like for folding commit relaxed R1CS. So as I said, the verifier only looks at things that are compact with respect to the size of the circuit. So we need to put the error terms and the witness in commitments and just read the instances, while the prover has access to the whole vectors of error and the witness. And the prover will compute some cross term that comes from the way like this folding equation extends, as I showed you, and send it to the verifier, because the verifier needs this cross term in order to fold the witnesses and the commitment to the witness and commitment to the error. And the verifier, of course, decided what's the challenge randomness that will be used in order to fold. Like this random linear combination will be done with the randomness coming from the verifier. Yeah. Okay, so let's see how NOVA folds. Like the NOVA paper that I mentioned has a way to folding that is different from what we propose in our flip construction. But it's interesting to see the parallel. So Nova starts with commitments. So now we look what prover does. Nova starts with commitments to the witness and commitments to the error vectors, many of them, right? And we can fold them in a tree, like each two witnesses using some randomness can be folded into a new witness, right? And so on. Sorry, like that. And so on till we obtain a final witness vector at the end and the final error vector. So at each step we interact. This is what the prover does. This is what the verifier does, where the verifier needs also the cross terms here. And of course, the verifier also needs to, and the prover, of course, needs to fold the initial statement and these U terms. Okay. So remark that folding with Nova requires the prover and the verifier especially, to look at all this commitment to the witness, to read as many commitments as the statements to be folded. So it's linear in the number of statements to be folded. Okay. And now let's see our flip construction. And for our flip construction, I go to more detailed technicalities. So I will need to introduce a bit the bilinear groups. We use the bracket notation and the additive notation for bilinear groups. We consider two cyclic groups, G1 and G2, where elements will be written in brackets with 1 and 2 indexes. And the bilinear map, which is the pairing, which I will call pairing, is this map that allows to take an element from the first group and a second group and sends it to a target group into the form of AB, like the logarithmic of AB, the product of the two initial logarithms. Okay, and these are the envelopes that I will use for each, like yellow envelope is for the first group, orange envelope for the second, and target group will be the transparent envelope. And what vector commitments we will use? So we'll use a vector commitment with structure setup, where the commitment key are powers of some tau value in the first group, as many as the length of the vector we need to commit to. And the commitment to a vector will be just the evaluation of the polynomial that defines defined by the vector with each coefficient corresponding to some power of x. Evaluated this polynomial, we can evaluate it using the linearity properties from the groups in this tau, without knowing tau, only by knowing the group element that encodes tau. Okay, so we have all the powers, so we can compute such commitments. And we need something more. We need to commit to group elements, to commit to this kind of commitments. So in order to commit to already existing group elements, A1 to AN, we will use target group elements. So we will compute pairings between A1, which is the element in group 1, and the power of tau corresponding to each position. So if we commit to n, we need up to n powers of tau. And this is an element. C is a constant group element, but it's a target group element that commits to group elements from the first group. Okay, and we need this commitment key to be in the second group. Okay, so now let's see how we are folding using all these techniques, all these commitments. So we start as in Nova with commitments to the witness vector and commitments to the error vectors. Here we have 4 different instances that we want to fold. And instead of folding them as independent values, we commit to all together. So here we have only one target group element that represents all the vector of witnesses we want to fold. So this is all that the verifier will see. And at the beginning of time, all the error is the 0 vector, because we start with the R1CS instance where the errors are 0, but each time you fold, the error will grow, so we'll have the relapsed R1CS appearing. Okay, so we have this commitment key that we use also in the second group, and we have these commitments, and at each step, we will do something like we do in a bulletproof like protocol or any inner product argument protocol. We will cut this vector into two halves and combine them together. So we will obtain a commitment at the end. We will show that we know a commitment of a vector half the size in which the previous vector was combined. So here we will have a commitment to W12 and a commitment to W34, which combine these two. And in total, there will be a target group commitment to a vector of 2 group elements and not 4 as the beginning. So each time we have a new commitment that commits to half the vector from before. And we continue like that until at the last step, we can have a commitment W prime here to a single committed in the first group element, this envelope behind, which combines all the initial commitments we started with, W, W2, W3, W4. So what it means is, like, at the very end, we can even open this commitment because it's not a vector anymore. It's only one group element, which represents some combination between the initial commitment. Okay. So remark that this is constant size for it's logarithmic size, of course, because we have logarithmic steps. But at each step, the verifier only looks at the constant size element, like just this commitment to the whole vector of initial commitments that the protocol folds. Okay, so that was the idea in order to save on the proof size compared to classical NOVA folding strategy, and to have a more efficient prover than in Groth 16 and SnarkPack strategy, because here we use exactly the same techniques as SnarkPack, but without proving anything, without any Groth 16 prover overhead at each step. So what we obtain after this folding between a prover and a verifier, we obtain this W final, which is the commitment to the final folded omega. And of course, if we take any commitment scheme with a commitment key that is not structured, we will need to have the verifiers in bulletproof check that the commitment key for each step was folded also correctly, because remember, at each step we have committed to a half of the vector, so the commitment key also has to be half the size of the initial commitment key, and this will be obtained by some same folding techniques. And in order to save on that, we apply the same kind of classical idea in this line of works, where is to have a structure key, as I showed before, which should be elements in the second group. Sorry, here is 2, and we use this target group commitment scheme. And at the very end, we just verify that the commitment key, the final commitment key, can be expressed as a polynomial using a logarithmic number of coefficients, like of challenges that we send along the way in each of the steps. So this polynomial can be decomposed only by using logarithmic number of coefficients. So the verifier can be logarithmic by just checking an opening of a polynomial in a random point instead of all the commitment keys. Okay, so the short thing that we did here is just this part. We folded the statements, and still we don't know how to prove. So that's what we will develop now. What is proving the final instance looking like? So now we have only the final instance, which is the final commitment to the omega vector, which is one element. It's not. It's just this commitment to the vector of one witness, and the commitment to the vector of one error. And what we want to prove is that the opening of this Z satisfies the relaxed R1CS relation. Okay. And if we use a generic SNARK, unfortunately, we also have to show that this is a valid opening E of some commitment in brackets. And the valid opening satisfies some committed relaxed R1CS, which will be a great overhead because we need to show a proof of knowledge of the vectors E and the vector W, which are linear in the size of the NP relation we want to prove. So in order to have this proof efficient at the very end, we need to tailor a SNARK for committed relaxed R1CS relation. And this is what we will do for GROT16. So we start with GROT16, which is the state-of-the-art proof system with the shortest proof that has a proof of 3 group elements, 2 in the first group and 1 in the second group, and also has a trusted setup that has all the powers of tau that I showed before, but also some other random elements, set of elements. And the equation, there is only one verifier equation, which involves 2 pairings, actually. Well, I'm lying a lot, like GROT16 looks like that. And the equation, it's this one, okay? With pre-computed, some of the pairings can be pre-computed, so it's 3 pairings to be checked, okay? And what we propose is a relaxed GROT16 scheme that allows to prove committed relaxed R1CS relations. And what's special about our scheme is that we managed to reduce all the, to make it the most efficient and to have the least overhead compared to the well-known GROT16. So like opening also 2 commitments inside the scheme, like showing that 2 commitments are valid to this vector, and these vectors E and W are part of this set that satisfy relaxed R1CS, doesn't require any extra group elements. Everything could be embedded in these 3 ABC group elements as the proof size. And we need an extra 2 pairings in the pairing check that allow to open the commitment to E that will come as an input to the R1CS, and the commitment to W that comes as an input to the committed R1CS. A great thing, like this is how our scheme looks like with these commitment keys for the error and for the witness. And the great things about our proof is like is the shortest committed proof GROT16 even with relaxed R1CS, but of course relaxed R1CS, as I said, it's a generalization. So if we set things to 1 and error to 0, this will become a commit and proof for GROT16. So it has small proof size. There is a prior work that does construct a commit and proof GROT16, and this is Lego GROT16, co-author here by Anna is here, and who has 2 additional group elements and 3 verification pairings. And in ours doesn't have any group element additional, but it has only 2 additional pairings. Okay, and this is for relaxed R1CS, not for simple R1CS. Also, what we obtain is 0 knowledge if the commitments are hiding, if they have a randomness, then composability between GROT16 for relaxed R1CS here, which is 0 knowledge with the hiding from the commitments for the witnesses, allow to have a hiding scheme, the folding scheme, which is not something that Nova can achieve. And we also do a very nice proof for the security of GROT16 in presence of some auxiliary input. And auxiliary input means that we take into consideration the fact that Flip has a trusted setup also, which are powers of some randomness. And as in prior works, we take into consideration that the ceremony to generate the trusted setup for GROT16 allows like leaks some other values, not the toxic base, but other public values that are not taken into consideration when proving GROT16 in the classical way. So we have a strong security model for this scheme. Okay. And yeah, I wanted to say that Nova also has an adaptation for committed relaxed R1CS for Spartan, which has transparent setup. Unfortunately, Nova, because Nova has to open and read the witness at the end, is not zero knowledge, and then prove it with Spartan. Yeah, and this is logarithmic proof size, while Groth 16 for relaxed R1CS is a constant proof size, but it needs pairing-based curves and is not trusty setup. Okay, I have some comparison between some approaches. Of course, SnarkPack was the approach we wanted to improve on, and we realized a great improvement in terms of prover size. Verifier is quite of the same, so I don't include the verifier here. And Flip also has zero knowledge, which SnarkPack didn't have. And also we explored the possibility of using Nova with relaxed Groth 16, compared with Nova with classical Groth 16 that should be adapted by rewriting the secret of a non-native relaxed relation into a R1 classic R1CS. So that has a lot of advantages. So our relaxed Groth 16 can be of independent interest. Okay, so I want to wrap up. So the summary of this is like, we use this idea of first folding instances, and we have a very efficient for the proof size and the verifier folding scheme via inner product argument in order to fold our statement. And at the very end, we apply only once the new scheme relaxed Groth 16 in order to prove the final statement. And this shows that all the original initial statements that were folded are also valid with respect to the relation. And our conclusion is that this can be better than recursion in some scenarios where we don't care about this overhead of the inputs or the instances that the verifier has to read, because we avoid all the expensive arithmetization of the verifier circuit. So we don't need to do the IVC kind of proof that some prior proof was correct. So this is at the cost of reading all the instances for the aggregated proofs. We don't need cycles of elliptic curves, as in Nova folding that had to do it because it has to write the Nova verification inside the circuit. So this was not optimal. We needed still cycles. And our relaxed Groth 16 can be used as an alternative to Spartan for proving Nova, which I think is great for systems that already apply Nova to R1CS proven by Groth 16. Some things that I swept under the rug is like this uses a lot of memory for the prover, so maybe we can improve that compared to IVC, where memory is saved because you only care about your current step of the computation. I also think that some extension may be interesting, and a lot of works were done to improve Nova for different arithmetization of computation, and maybe we can use same techniques to have this flip alternative to them. And also, we need better curves in order to apply this relaxed Groth 16 to Nova last step. I think Nova uses a cycle of curves now, so then there will need to be something compatible with the cycle of curves that also have pairings in order to do Groth 16 on top of it. So those are my open questions. If you have any idea, I'm happy to chat more. And thank you for your attention, and happy to take more questions, of course.
Thank you, Anca. Yeah, we're just in time, but I think we can spend maybe 5 minutes to have some questions.
Yeah, I also wanted to double check if the things I said about Lego Groth 16 are correct, like the commit and proof Groth 16.
Yeah, it's fine, thank you. Well, I actually had a question regarding one thing you said at the end, because you said maybe like a future line of work could be to try to generalize it for other systems that are not necessarily R1CS. So I was wondering if there's any kind of property that you think those other type of constraint systems would need to satisfy in order for this trick to work, or maybe you think you're pretty confident that maybe it could work easily for Plonk or for any other thing.
So yeah, that's a good question, but I think a lot of work was already done by all these follow-ups from Nova paper that already consider a relaxed kind of version of the systems, of the constraint system, so they can fold them. So for the Plonk, they have something in Sangria, and there is this CCS generalization of both R1CS and Plonk that allows for folding because it has already a structure that has some error in the definition. So I think that will not be the difficulty. I think like things we can lose when we generalize is some of the systems don't have trusted setups, and those ones may be hard to fold with the same techniques where we really need to commit to things with a trusted setup. So we have to add some trusted setup for it.
Okay, makes sense.
Yeah, go for it.
I don't know if you want to go first. Or...
No, I was just saying you can just talk. Yeah, don't need to raise hand.
One comment just about the generalization for Plonk and others. It's just if you want to have custom gates with higher degree, you just generalize the polynomials to be homogeneous, and everything works. So you've got more than one cluster. So if you've got like polynomials of degree 3, you're going to have 2 clusters. If you've got custom gates of degree 4, you're going to have 3, etc. So I don't know if it can be easily generalized with your work. Yeah. And I don't know if Proto-Galaxy or Protostar does do that. I don't know enough about it.
Yeah, I didn't look at it, but I think they did a lot of things before, like in this direction. So I will, hopefully, I think that most of the things will be useful for this generalization.
I had a question when you said that you need to add trusted setup. You're referring to the powers of tau that you need for the inner product?
Yes, exactly. Like for the verifier that is sublinear in a linear.
Okay.
Yes. And also, yeah, maybe we can explore other techniques if the witness is committed in different forms. I don't know what commitment scheme we can look at for the witness. I guess all the prior work are still looking at some Pedersen-like commitment, but yeah, I wonder if we can use Fry or something else for that. Because our target group elements are commitment to already committed witnesses. This is what I'm...
You do use the homomorphism of commitment in your scheme, right?
The one over target group elements, yes. Yeah.
Okay.
I do have another question, Mark. Are you done or not? I'm trying to judge by your face.
Yeah, go ahead.
Sorry, yeah, I also had another question, just more of just trying to conceptualize this work. So it's not really fair to compare it with Nova, right? As far as I understood, it's not really fair because Nova is used for, Nova can be directly used for an IVC solution, right? So if you want to prove that like your function f executed on itself like 10,000 times, it produces a certain result, Nova makes it fast to verify that result. But in your particular case, I think with the flip-and-prove, you would need to have all the instances for the intermediate communication, because you can't really do this IVC. You can't. You don't really judge the previous fold in your current circuit.
Yeah.
Because your target group is pairing based, so you can't really it would be really expensive to embed that, right? That's my understanding. So
Yeah,
this is for like when you have all the instances, a linear number of instances, and you don't want to compress that, but you still want to prove them. Is my thing correct?
Yeah, your observation is correct, and I think that's the main difference, and that's why we target kind of different setting, because in Nova you have them separately, so you can fold them, even do this in parallel, right? And IVC comes from rewriting the relation for each you fold, which includes the check the previous folding was correct. Like the verification of Nova folding is inside the relation, which is why they need cycles of curves and things like that. And in our case, we aim more at some aggregation kind of the statements. We start with all of them. So at each step, we need to have all of them kind of, and this saves on the verifier looking at all separate. But of course, all the inputs should be kept, because we don't verify recursively anything about prior statements. Like we treat them kind of equally at one level. We have all these statements for one level, and then we fold, and then we can forget the level before, but not in parallel as in Nova, which is a nice feature that you can do two of them, and you drop these two and you continue later. In our case, we need to keep all the level, the base level, and then start folding. Yeah.
Yeah, gotcha. Thank you. Okay, any more questions for Anca? Well, if no one has anything just now, I invite everyone to thank Anca again for joining the seminar, and we'll see each other in 2 weeks. And let me stop the recording for now. Thanks, everyone.